We have one more pattern you have to keep track of, and then I think we're pretty much done here. The factoring a difference of squares expression looks a little bit like what we just did, but it is very, very different. Notice that we only have two terms to factor now. The binomials that we end up with are similar, but the middle term always drops out when you FOIL it back. So keep track of this. We have a difference of squares, but this pattern only has two terms. When we factor it, we get two binomials that look very similar, but the signs of the binomial's second term is opposite. So if you have a squared minus b squared, that means you have a perfect square minus another perfect square. When you factor that, it will always come out as two binomials with the second term positive on one and the second term negative on the other. We have y squared minus 100. This is a perfect square minus another perfect square. So this will always factor to y plus 10 and y minus 10. If you want to check it, go ahead and FOIL it back. In fact, let me just do that for you right now. First will be y squared. Outer will be minus 10y. Inner will be plus 10y. And last will be minus 100. Notice that when I combine my middle terms, those go to 0. And you could also say 0y if you're curious. So that would be y squared minus 100, which is what I came out with. So this is just a check to see if what I did worked. And it did. Yay. Moving on. In the next exercise or expression, we have a to the fourth minus 81. And this will be a perfect square, but it might factor more than once. We'll have a squared and an a squared. We'll have a 9 and a 9. One will be positive, one will be negative. Notice that the a squared plus 9 would give us complex solutions, so this one just sits here. But a squared minus 9 does indeed factor further. This a squared minus 9 would factor to an a and a plus 3 and a minus 3. Rewriting all my factors for a to the fourth minus 81 would be a squared plus 9, a plus 3, and a minus 3. Let's take a look at b here. We have a squared b squared minus 36. I can factor that to an ab and an ab as my first terms, and a 6 and a 6. Since the middle term is negative, I know I need a positive and a negative second term. In part D, we have 18a to the fourth minus 50a squared b to the fourth. Taking out a common factor, I will take out a 2 and an a squared. This will give me 9a squared minus 25b to the fourth. Factoring further, we will have two binomial factors. Don't forget to drop down your 2a squared. We'll have a 3a and a 3a. We'll have a 5b squared and a 5b squared. And then, since our middle is negative, we'll have a positive and a negative inside those two binomials, respectively. Now this last term, it looks a little tricky, but just think of p plus q in the grouping symbols raised to the second power as one term. P plus q as one term. So we have p plus q squared minus 25, and I'm just going to keep that p plus q grouped inside parentheses. I'll write this as two factors. P plus q I'm going to keep as p plus q in parentheses, and I'm going to rewrite it p plus q as my term in both binomial factors. I know they're not binomial factors, but that's what we call them. and the p plus q is still in parentheses. I kept it grouped. I'll have a plus 5 and a minus 5 here. And now notice that I could drop those parentheses now that I've factored it. So the p plus q stayed in parentheses until I was done factoring, and now I have p plus q plus 5 and p plus q minus 5. The last thing we need to cover is equations and functions related to these patterns for difference of squares and perfect square trinomials. It looks like we might have a perfect square trinomial right here, but we need to factor out the GCF 2 first. That will give us an x squared minus 12x plus 36 equals 0. And then factoring that trinomial, we'll have 2 out front, an x and an x, a 6 and a 6, and since the middle term is negative, we'll have a minus minus. Now, if there had not been a middle term in there, then we would know that it would be factored as a difference of squares. But this is a perfect square trinomial instead. Now, the x squared minus 64, those are both perfect squares, and it is a difference of those two squares. So we know that we can factor this so that the middle terms will drop out. We have an x and an x, an 8 and an 8. We need a plus and a minus, so the middle terms drop out. And my solutions will be x equals negative 8 and x equals 8. For this other first one, I always jump ahead and I forget my solutions, and then I have to go back. But my solutions for this equation is x equals 6. So my repetitions, we call this a multiplicity, but you can just say x equals 6. Now we need to find the zeros of the function x squared minus 8x plus 16. Well, I'm going to set that equal to 0, so f of x equals 0, and then that is equal to x squared minus 8x plus 16. Therefore, I need to factor that perfect square trinomial and set it equal to 0. That will be an x and an x, a 4 and a 4, a minus minus. And so my solution is x equals 4 with multiplicity 2. On this last exercise, we have f of x equals x squared minus 12x. Find a such that f of a is equal to negative 36. We'll rewrite this as f of a is equal to a squared minus 12a, and then we know that f of a equals negative 36. So I'll replace the f of a with negative 36. That will be an a squared minus 12a. That's what it's equal to. And then I need to set this equal to 0. So I'll have a squared minus 12a plus 36. This looks like a perfect square trinomial, so it factors to an a and an a 6 and a 6. My middle term is negative, so I'll have a minus minus. That means that a must equal 6 for this statement to be true.